So last class, I think the first class, which is the introduction to VLSI design, I think you people have missed it. Uh, so Professor Dhar has given something introduction regarding digital design, and I will cover something briefly the digital introduction to digital design, digital VLSI design. After that, we will go to the Verilog HDL. So very briefly, I present the introduction to the VLSI design. So basically, the present days, the digital VLSI design is broadly divided into two, like FPGA and the ASIC. Okay, the digital implementations is taken by the two implementation. One is FPGA and ASIC. FPGA stands for the field programmable gate array. Field gate array. Okay, where ASIC stands for the, I will tell you what is the difference between the FPGA and ASIC. ASIC stands for the application specific integrated circuit. Right. So FPGA, like it is a you will have a chip, right, and you have to reconfigure the chip. I think you might have heard about the microcontroller, right. Similarly, it is a the chip is already there and cells are already fabricated, and according to your design you have to configure your FPGA chip, right. But ASIC is a, it is application specific integrated circuit. So what you do the design, that finally you have to fabricate. So basically you will find FPGA is a more semi custom design and ASIC is a full custom design. So according to your design constraint, design requirement, you can fabricate using the ASIC concept, ASIC flow, basically ASIC flow. But FPGA you cannot do. The FPGA chip is already there with particular technology. So when you implement your design on FPGA, you will have a performance according to that chip. You will not get your performance maybe in the terms of speed. But ASIC, if you go through the ASIC, if you want to target a particular speed, so then you can have a in a ASIC design flow. Okay, so this basically in the digital design in FPGA and ASIC, we will have a steps. Say from the, you have a specifications. So suppose you want to implement a one system, right, to a chip. You may fabricate the chip using the ASIC, or maybe you implement through the FPGA to get a functional, your desired function. So you will have a specifications, like in terms of how much speed you require, how much area you require, how much power you require. So you have to decide, and what is the functionality you should have. So that is specification should be there. From the specification, through the design steps, all design steps, you have to finally fabricate the chip, fabricated chip. Okay, I think yesterday class the steps already given. From the specification, we will have an algorithm to the architecture, right, architecture to the gate level. Okay, from the gate level netlist to the physical design, and from the physical design you have to tape out your chip, get the GDS2 and get the fabricated chip. So this is the basically steps for the design. So broadly speaking, these steps are two steps. Okay, one is the front end design, the designer the front end design. Front end design, what is the front end design? I mean, you have a specifications, you get your suitable algorithm and choose your efficient architecture. Okay, the architecture you code or you draw in the schematic and generate your netlist. Okay, so that is a gate level netlist. You are getting the gate level netlist. So the front end design is broadly speaking the specification, algorithmic analysis and architecture design, and you once architecture design is did, so you have to verify either manually or computationally you have to do. So that things you will take care of now. And after you got okay your architecture will working fine, after the verification, then you go for the synthesis. I think synthesis the next class we will study about the synthesis. I am not covering synthesis. So in the synthesis what you do, you will get the net list of your circuit. Okay, this net list, after this logic net list, you will find the specification to the logic net list is your front end design. Once you will get the front logic net list, you take the net list and go for the physical design. What physical design consists? Physical design, you have to like floor plan the chip, floor plan where like how it looks, the floor plan you have to do the floor plan, and where your blocks should be present. So you do the floor plan, like when we are constructing the house, you should have bedrooms should be there, kitchen should be there, toilet should be there, no, your drawing hall should be there. So like that you have to plan your places where you put your logics, say memory in terms of digital design, where you will put the memory and where you will put the logic blocks. Okay, so how you will put the gates, so I mean doors, where, so this requires the something efficient design. So if your architect is fine, okay, so you will get the efficient area, you can say. Okay, like that in the design also you do the floor plan, right? So backend design, backend design broadly classified, first step is floor planning, second is placement, I mean you did the floor planning, okay, so inside you go to the where you will place the cells. Okay, how do you place the cells? Say in the room, how will you put your almirah, no, where you put the shelves. Okay, you have to decide those things. Okay, so that is how to place the your cells, logic cells. So that is a placement. And the third is you can say routing. So how you connect the cells efficiently. Okay, so that these things will take care of the physical design, backend design, and that is third step is the routing. Okay, once you do the floor plan placement routing, then you verify your logic, okay, it is fine, then you have to generate your net list, physical net list, that is called GDS2, that is industrial standard GDS2. So this GDS2 will go to the fabrication. So these are the basically broad part of the backend design. You will study detail in that class. I am not going through, because our like this class is related to the front end design, that is in the simulation level. So now I think you studied about the architect design. Once you got your algorithm, and okay, before that I meant to say like FEJ, I forgot about the FEJ. Unlike this, basically what I talk about this front end design and the back end design. These are specifically ASIC flow, right? In the FEJ flow, what is the FEJ flow? FEJ flow, like very similar. The front end design is similar to the ASIC design and FEJ. Okay, only the difference is the backend design. Okay, so the tool in the basically in the FEJ design, and the Xilinx and Altera, these are companies, those are providing the FEJ and the CPLD. So front end is more or less equal, I mean same to the ASIC design and the FEJ, only the backend, because backend is a totally technology dependent. Okay, I mean up to the architecture design is the same. When you go to the synthesis, okay, synthesis according to which library you require, that is technology dependent. So that depends upon your which ASIC you are going or FEJ you are going. So front end is basically the same for the ASIC and FEJ, but back end is a different, that depends on the technology. Okay, so in the steps, like we will talk about the front end design. I think you last class architecture design is already given to you. So then architecture design, what is architecture design? I mean you are getting your suitable algorithm from your specification, what functionality you are having. So from the algorithm you are mapping to the architecture, that is a block level architecture, right? So what will happen? So say suppose this is a typical, I think you are, yeah. So this is a typical architecture, say where we are having the controller logic and main logic units, say main common bus and some control signals. I will give a case study similar to this architecture. I mean this IC, very similar as a case study I will give you. So basically, in the flow, in the tool, if you talk about why you will go for the EDA tools, right? These are the EDA tools. I am talking about the EDA tools. Why you will go for the EDA tools, right? So before you see, if you think about the history of the digital design, so we will have a SSI, small scale integrated circuit, where you need only few transistors or maybe a few gates. Then MSI came, then LSI came, and VLSI came. In the VLSI, you need a million of transistors to put in a chip, right? So see, in the SSI case, the few transistors are there or few gates are there. So you can do manually the things designs. Okay, I can design this way manually. I can do the layout. How you are doing the analog design, right? Few transistors, suppose you are designing a differential amplifier, say 2 to 4 transistors is required. So manually you do the schematic and you do the layout. So manually you can do. But when you are talking about a million of transistors, I mean millions of gates, it is not easy to have a manual design. So you have to take help of the software. So for the digital design, we are having a EDA tools like electronic design automation tools, or you can say CAD tools, computer aided design tools, EDA, or you can say CAD tools. Right. So in the tools in the digital flow, basically we are having I told about the front end, the back end. Basically the design entry, we will have a cadence tool in our lab, that is a Verilog XL from the cadence, where you use the HDL language. I will talk about the HDL, and you do the simulation using the sim vision. And once you got verify your functionality, this Verilog XL and SimVision is used for the verifications, like design and verifications. And once you design your, I mean textual mode, HDL is a textual mode, and you go to the synthesis where you require the design compiler, and we are using the design vision. And then design vision, you get the netlist, get level netlist. I mean this synthesis part, and get the netlist and take the physical design. In the physical design, you are using the SOC encounter from the cadence, and we are having the IC compiler also and Astro also. I don't know which tool you will be provided during that time. So mainly SOC encounter we are using. For the physical verifications, we are using the Hercules. Okay, this is the typical design flows using the EDA tools. We are using these EDA tools. Okay, so now you come to the once you got the architecture, right? So the architecture, what you got, multiplier or maybe registers or maybe adder, like you have studied that yesterday, that is architectural mapping, right? You have a registers and maybe adders, right? So what you do, like when you are going to the EDA tools, you are not doing manual now. You have to take the help of the EDA tools, right? So in the EDA tools, so how you will enter into the EDA tools? Either you go to the schematic, how you are doing the analog design, okay, or you have to go to some textual mode. So basically, the design entry we are having, say HDL and schematic. schematic. Why you will go to the first HDL? HDL stands for the hardware description language. Hardware description language. HDL stands for the hardware description language. You see, we are having the C Fortran, right? We can write also C and C plus Fortran, but this C and Fortran, you see, you know that C and Fortran, these are a sequential compiler, right? The execution is a very sequential, but digital design needs some concurrent process. It requires some concurrent parallel process. So this Fortran C will not help us, right? So what people thought, okay, you will design something language which will do the concurrent process. So HDL came up like C, and they executed with the concurrent process. After that, people has standardized the HDL for the hardware design. So now the hardware HDL is a very popular. Broadly speaking, this HDL is divided into the two parts. One is the Verilog HDL and VHDL. Okay, this HDL, I mean, we will talk about the more I will talk about the Verilog, not VHDL. You can study similar to the Verilog. VHDL stands for the very high speed integrated circuit HDL. V stands for very high speed integrated circuit. VHDL stands for the very high speed integrated circuit integrated hardware description language, right? So we are having the broadly two languages for the EDA tools, where the EDA tools take care of this tool after standardizations. Okay, so now the question is, why you will go for the HDL, why not for the schematic? You are doing the schematic in the analog. I told one thing is, like schematic, it is not possible when you will do the millions of gates design. So that time HDL is a very textual mode, so you can do it. So main difference between HDL and schematic, HDL is a textual mode like C, right? Whereas a schematic is a graphical mode. Graphical mode, right? Second is, schematic is a technology dependent, right? When you are doing your simulate which you are ICFB you are using, right? In the analog, you will find instead of transistor you have a gate libraries also there, digital gate libraries. You can use the gate libraries, right? So those components are very technology dependent. Okay, so schematic is a technology dependent, whereas this HDL textual mode is a technology independent. So now what you conclude? Another thing is, when you are doing the schematic and HDL, if it is a millions of gates you are describing, if any changes to be done, then schematic is a very tough. In the Verilog, it is a interactive. You can analyze. Okay, it is very easy to edit the textual mode. Okay, that is advantage in the HDL. Another is very advantage in the HDL and schematic is, schematic is I told schematic is a technology dependent, and suppose you are designing with a particular technology, say 0.18 micron technology. In the future, same design you have to implement in the say lower 0.065 micron technology, right? So you cannot change the schematic. Then again you have to do manually, right? So I mean, schematic is a very specific to a particular technology. Okay, but if you design in the textual mode, HDL mode, if you design in the HDL mode, so suppose you are changing your technology, there is no need, you map to the particular technology. Okay, say if you design 0.18 and further you want to the 0.065 micron technology, so same design you just map to the that technology. So synthesis tool is available for us. So synthesis tool will take care of. So basically, what you conclude, the HDL design is a portable. Okay, whereas a schematic is a not portable. Right. So these are the difference between the HDL entry and the schematic entry. Now we will focus on the Verilog HDL. The history of the Verilog HDL is like that. This Gateway Design Automation is a company who started the Verilog HDL in year of 1983. The concept came in the 1982. Gateway Design full-fledged it is used in the 1983, and after that in 1989 Cadence took up the Gateway Design Automation and pushed in the public domain in probably in 90. Okay, after that it is standardized for the IEEE standard. Till that we are using the Verilog HDL. Okay, so this is the history of the Verilog HDL. This is no use of for us. So now we will come to the actual what are the syntaxes in the Verilog HDL. This is a language, textual language. So we have to study about the syntaxes. Unlike C, we are having some syntaxes, right? Say main and integer, variable, real. No, those things we are having, right? So similarly, we are having the some syntaxes like before the syntaxes, some identifiers and what is the logic values. Mainly we are having the keywords and identifiers. Okay, so like we are having the C, say suppose you are declaring an integer, right? Integer int, you are declaring the int, and some variable you are giving name, some name you are giving x. Okay, so int is a keyword for the C and x is a identifier. X is a integer is a keyword for the C and x is a identifier. Similarly, in the Verilog we are having the keywords. Keywords I am not covering the all the keywords. I will talk on when you can realize what are the keywords and what are the identifiers. So keywords, say suppose we are having a keyword typically race, say suppose in a value say data or value you can say so input and data. So in the Verilog, race and input are the keywords and value as a data is a identifiers, right? So basically Verilog, you keep in mind, Verilog is a case sensitive. Okay, Verilog is a case sensitive and all the keywords are the small case. Okay, so another is what is the constant on the identifiers. Identifiers I have told the any sequence of letter, digit, dollar sign and underscore, and first character must be a letter or underscore, not the numbers. When you assign the identifier value, data or kind, it can be any digit or letter or be dollar or underscore, and first character should be a letter or maybe a underscore but not a number. Problem constant is, and the first letter should not be a first character should not be a dollar sign, because dollar sign is reserved for a system task. Dollar sign is reserved for the system task. I will talk about the system task in the later. And cannot use a character such as a hyphen, bracket and hash, because this is used by the compiler. Okay. And typically in the because we are talking about the digital design, basically we are having the 4 logic values, that is 0 for the low, 1 for the high, okay, x as usually don't care, and Z stands for the high impedance state. High impedance state. So these 4 logics we are using in the Verilog HDL. Now, like a data type in the C, integer, real, okay, like that, we are having a similar data types in the Verilog. So that type data types here, some of them I have written here. That is a integer. If you declare as integer, you can have a keyword integer, right? And similarly, we have a nets, because you need to connect your components. Okay, nets, you have a keyword. There is keyword like net. Net and wire, I will tell you what is the difference between net and wire. Net is a keyword, like wire is used as a keyword for the nets. Okay, when you are connecting the components, that time you require the nets. And the registers. Registers means like a variable in the C. Here the register is to storage the temporary storage. Temporary storage are variable similar to the high level language. I mean, it is just for the storage, not like a register. You may register means you talk about the registers, right? Digital people will know registers means the flip flop. It is not a flip flop. It is just a variable to store the values unless the value will not change. Okay, and wire is a analogous to wire in a physical wire. That is a wire connecting the components. Also, this is a wire, block to block connection. This wire, that keyword is a wire. Okay, in addition to this wire, this data types, we are having the say vector. We are having the vector, right? Array is also data type in the C, and we are having a memory. Okay, what is the vector over here? Vector means, suppose you will take a 1 bit, that is a scalar. Okay, if you assign a variable with a multiple bits, say 8 bit, so how will assign 0, maybe 0 to, say suppose 8 bit, or n bit, you can say 0 to n. So this multiple bits is called the vector, right? And array, what is the array? Array is the multiple elements should be there in the array. Similarly, we are having the multiple input. Say suppose one variable, we are having the x, having the 8 bit. So how you will declare? X is a variable, I mean x is a vector variable which is presented as 0 to n. 0 stands for the LSB and n is the MSB, right? Least significant bit and most significant bit. Array, you have to declare, say array is a multiple elements. Okay, so multiple elements means, suppose I am having the array y. Y contains, say 24 elements. So how I declare? I have to declare, sorry, the n equal to 0, this vector actually define the right side x, okay, not the left side. And y, when you are declaring array, you have to declare array contains the, say 24 elements. So y you have to declare as a 0 to 23, right? So y is a array is having the 23 elements, sorry 24 elements, right? And if you assign, there is no bit, there is no point, not bit assigned, so by default it takes the, so okay, before if you talk a vector variable x, so suppose you declare a variable x, then it will be x is a, I told register is a variable, right? So for example, I will declare a register is a variable and x, okay, then it is a single bit variable, right? It is a single bit variable. Suppose I will write as a register n minus 1 0 x, then is a x is a variable of n bit. Okay, similarly array is like that. if you declare as a variable say y say 0 to n minus 1, say 0 to n minus 1, say n elements are there. Okay. Say array, say I will declare the variable race, right, race, and having the array name y, right, having the say for example 24 elements I am having. So I declare as a 0 to 23, right, and if so what is this, if I don't assign any bits, multiple bits in the left side, I will treat as a, it is a 24 elements is having a single bit, each element is having the single bit. Suppose I will assign the bit in the left side like register of vector, like say suppose I have 3 0, I will declare like this, then it will be a 24 elements of the each element is a 4 bit. Okay, this is a array, I think just like a C. And a memory. Okay, in the memory is the array. Memory is nothing but it is like just like a array declaration. Okay, so how to access your this memory? So suppose I am using the memory declaring arrays, say 8 bit, each element is a 8 bit, say memory byte, I am using the memory byte, say I am having the 23 elements, 24 elements. Okay, so I want to access read and write operation I have to do in the memory. I think this is the assignment to in the end, how to design a memory model. So what you do here, suppose you want to access the 7th byte, 7th locations. So what you do, you have to declare as a memory, I have to write a mem 7. Okay, this is the address for a particular memory locations. Okay, so this way you can declare or model your memory. This is assignment for you, I am telling in the beginning. Okay, so now comes to the basic things, like basically Verilog. How is the memory different from array? No, memory and array is not a, this is I told memory is similar to the array, no difference. In the you see when the Verilog is a very design is a modular concept. Modular concept means what? We having a approach, two approach. One is a top down approach, I mean hierarchical design. Hierarchical design, we are having the top to down approach. Okay, and another is a bottom up approach. What is the top and down and bottom up? So top and down is like this. You have a algorithm, right? You design your block level architecture. Okay, so block you have to subdivide it into the sub blocks. Again, sub blocks is divided into the still sub blocks till the cells where the blocks, I mean that blocks cannot be divided further. So mean we have a block, right? You divide to the sub blocks, maybe another sub blocks is there. Okay, sub blocks again you divide to the again further sub blocks. Okay, still you come to the leaf cell, I mean where these sub blocks cannot be further divided, modularized, I mean not divided. So this is called a leaf cell. These are called leaf cell. So you come to the top to the bottom. Okay, now once you will come to the bottom, you design the bottom leaf cells and integrate to the top. Okay, so this is a top to bottom. Again, you design all bottom level cells and go to the integrate to the top level. So again go up. So that is called bottom to up design, bottom to up approach. Okay, these are the two like modular concept. So now the main thing we start like so suppose you are having a block, you have to describe in the Verilog HDL. Okay, so in the digital design we are having a ports, right? Pins you are having, right? Physical pins. I mean ports you are having. Logical things you talk about the port, and physically you talk about the pins. So we are having the input ports, output ports, and in out ports, right? So I think you might be seeing over there. So before going to the black box, say suppose what is happening in the block, this box, we will not bother about now. That is we call a black box. What functionality does, we don't bother about now. We will describe that later. So main thing is how to define a module. I mean how to define a this black box. So for that we have a ports. So how to declare these ports? So unlike you are having the C, when I C you find the main, right? We are putting the main, right? If a void kind of stuff is there, again you are starting with the curly bracket. That algorithm you are closing with another curly bracket, right? Similarly in the Verilog we are having the module and module. So everything you have to describe between this module and end module. Okay, like curly bracket you have to describe module and end module. Clear? So now what are the syntaxes? How to write the syntaxes between module and end module? So broadly speaking, this module declaration, I mean this is a module name. So you have a module keyword module. So you have to declare your module name. What is your chip name? You have to declare your chip name. That is called module name. Module name. So module name, and you have to declare what are your ports, input ports or output ports and in out ports. So you have to inside this you have to declare your ports, right? So suppose you are having the flip flop. So DJ, DQ, reset, clock, these are the ports. So you have to declare D, clock, reset, and maybe D out or D out bar, like that. Okay. So you have to declare, and after that the main syntax starts like the port type declaration, whether it is a input port or it is a output port or in out port, right? So this I think in this bracket you see the input and type, input and port size. I already told the variable vector declaration. So you have to declare your port size. So suppose it is the 8-bit, then 780, and what is the input port names? Input port names. Say suppose in the flip flop I am input pin is say D. Okay, so I will not use like a vector D. So maybe another say X. Okay, so X is a input name, okay, and having the 8-bit. Similarly output you have to declare input and output and in out. Okay, I am not telling on detail, I already declare. So then you have to declare the wires and registers. What is the role of wire and registers? In addition to your input and output, when you are connecting the, because you have a sub blocks also, right? Blocks and sub blocks. So sub blocks you have to integrate, right? So during the integration you require the wires. So you have to declare the wires necessary for the connections. Okay, necessary wires for the connections, integrations or connections. So register declaration. I told during the computation you require some variables, temporary variables. Okay, so that's temporary variables you have to declare a register as a register. So these are the declarations. Okay, now you come to the black box description. You declare, okay, what are the input type and what are the voids and what are the registers you require, what are types, and you come to the now the actual design process, how the architecture behaves. That is a black box descriptions. Okay, that box we don't know how it will work out. So how to describe the black box. Achha. Before to the black box design, I will tell you one thing. Still I am not getting to the black box design or description. Another important thing is when you are doing the integrations, subblocks to subblocks, I mean the module to module, how you have to connect it. Okay, after that we will go to the black box descriptions. That is, you know, the connections, okay, or module integrations we call as a module instantiations. What is a module instantiations? A connection of the module. So suppose we are having the module name 1, say module 1. I have written here module name 1 and module name 2. Okay. So module 1, the syntax is like that. You have to declare something module name 1. So that module, that keyword you have to put here in the module name 1, and you have to give the some instances name, say instance name 1. Okay, and you have to connect it. So the port, you have to do the port connections. So basically the port connection is two types. One is the by position and another is the by names. When you are connecting the ports, how will you connect it? What is the technique used by the Verilog language? So we are having two techniques. One is the by position or ordering. I mean position ordering means the you already declared a module, right? Say module you are having in the module say X. Okay, I am having the module say X1. I am having the module X1, and ports I have declared say X. Say suppose how I will give say D Q say R. Say suppose I have given the DQR, maybe input output I am not bothered, this order I have put, right, and I am having another module say X2. Okay, this is the having order of say P say S say T. Okay, so these are the orders, like I have to connect in this order only. DQR I have given the one example here, don't bother about, just simple for understanding given here. I have in the slides I am having an example. So these modules I want to connect it. So how I will connect it? Either by position or by the names. Say sorry. So for example, this is the sub mod, this is the block. I am having the three modules, mod A, mod B, and module C. And you are no, yeah, correct. So this, sorry, yeah, this module A, module B, module C, we have to connect it, right? So what is, these are the input in0, in1, in3, and out is a port declaration I have done in the top module. This is the top module, and I have this top module contains the three modules, and you know these are the connections. We have to do the connections for the sub modules. Okay, so there is a, I have to declare the wire, so that is a W1 and W2. These are the two necessary wires to be connected, W1 and that I have to declare, that is a W1 and W2. Okay, now how to integrate it? Okay, so for the integration, suppose I will define a module A, module B, and module C. Module A is having the name of A1, A2, A3. Module B is the ports having the B1, B2, B3. Module C is having the port of C1, C2, C3. So how to integrate this module A, module B, module C, right? So in the top module, when you connect it, so you declare the input and output. I told this is the wire you have to declare. I need the W1 and W2. This W1 and W2 I declare, so I have to connect the module A, module B, module C. In the module A, module B, module C, so this is by position. I mean, you see module A, for example, module A, how I have declared A1, A2, A3? You come a module A first, you will go to the BC later. A, the order is, position or order is A1, A2, A3. You see how A1 is connected here? A1 is connected to the in0, right? And in A2 is connected to the in1, and A3 is connected to the W1. So I will put just in place of A1, A2, A3, I will connect the En0, En1, in1 and W1. This is the by position or by order. And similarly for the module B, and similarly for the module C. Now that it is integrated for the top module. This is by the position. Clear? By the name syntax is like this. Dot A1, I mean, what is the name of the your submodule where you are connecting? Dot A1, the module name, I mean port name of that module, and where that I mean inside the bracket where you are connecting, that is a in0. Okay, dot A2, a in1. Okay, dot. See what is the difference position and by name? The difference is like that. If this order, say suppose you put the dot A2 first and dot A1 next, second, it will not matter. It will be the correct result. If by position, if you design, you connect your modules by position, if your order will change by mistake, the gone case. So you have to take the precaution when you are doing the port connections. Okay, but in the if you go approach like the port name, if this order does not matter where you will put it. If you put dot A1 in the last and dot A3 the first, it does not matter. But in port connection, if you interchange any port, then gone case. Okay, so this is the port connections. Now you come to the black box design. This black box design, we are having the how to describe the black box design. So we are having the four approach, four abstract levels. One is the switch level descriptions, gate level descriptions, data flow descriptions, and behavioral descriptions. So the topmost description is, and highest abstract level is behavioral description. This is the highest level, and the lowest level is the switch level descriptions. So from the we will start from the lowest to the highest: switch level, gate level, data flow, behavioral. How the black box, the functionality of the your module works. How your functionality of the architecture or module works. How we will describe so that the you will get your functionality. Okay, so we are having a different four abstract levels to describe your design, right? So these designs we will go by one, switch level. First we will go in the switch level design. Basically, we are using the transistors, right? So this is the transistors we are having the PMOS and NMOS. Okay. So suppose I want to describe this PMOS and NMOS, and for example, I want to design an inverter using this transistor PMOS and NMOS. Okay. So now what you do, you have to declare a module. This is a module name. Say I have given the CMOS inverter. What are the inputs? Of course, VDD, ground, in and out, right? And you declare your input and inputs and outputs, right? And what you do, you have to do the connections, right? You have to connect this these transistors. So in the most of the compiler is having the keywords for the PMOS transistors, that is a PMOS. Okay, for the NMOS, that is a NMOS. So now these keywords, these components, this is a PMOS, you can say primitive, compiler primitive. This is PMOS and NMOS. So you now you do the connections. I think it is clear. I have done by the positions. Is it clear? That say PMOS. PMOS is connected to the VDD in and out. Right. The connections basically the compiler does respect to the source, drain, and gate. The order because we are doing the by positions, so you have to be careful about it. So basically the order of the ports in the PMOS is the source, gate, drain. Sorry, source, drain, and gate SDG. Right. So now the source is connected to the PMOS is connected to the VDD, and so like drain is connected to the out and gate is connected to the in. Okay, right? NMOS is also similar way. Now I design the inverter, I model my inverter, right? This is a switch level. After designing your switch level, I mean bottom level, you go to the macro module designs. Okay, maybe you using this transistor level design, you go to the gates, say NOR gate, NAND gate, NOR gate, and different AND gate, XOR gate, XNOR gate, like that you have to design. Using this, maybe you may use a transmission gates. Have you heard about a transmission gate? Okay, leave it and you will study. So these are the basically gates, and you may be top level, maybe macro modules like adders, subtractors, multiplexers, and flip flops. Okay, this way you can go to the bottom on a top level design. Okay. Now come to the gate level or structural level design. It is very similar to the structural level design. There we are modeling with the transistors. Okay, here we are modeling with the gates. We are modeling with the gates. So this is simple multiplexers, right? This is, I think this is the multiplexer logic, right? Right or not? It is multiplex or not? Yes. Okay, fine. So then the multiplexers is having the gates like 2 AND gates, 1 OR gate, 1 inverter. So we need a declaration wise F1 and F2, right? And inputs are the A, B, select, and F, right? So now what are the wires we require? N select, F1 and F2. So you declare those things. Now what you do, like and or not, these are the compiler primitives. So you can use and or not, okay, and do the connections. And what is the connection how to? I told you should have a module name or a primitive name followed by the instantiation names. Okay, you keep in mind when you are declaring the you are instancing the same module or same primitive, instantiation, I mean module name may be same, will be the same, but this instance name should be the difference. Otherwise, compiler will give the error message. Okay, this instance name should be the difference, unique. This instance G1, G2 should be the. You cannot give the G1 and G1. It will not take. Okay, this should be the unique. And similarly, you can connect your ports, right? So like that, you can do your structural design. Clear? So suppose this is the multiplexers. These are the, I am not using any delay, right? So suppose I design a one model is having the concept of delay model I am using. Suppose, say for example, in this case, say suppose I am not giving this example, say and I am having the gate of say maybe OR gate connected this way, A, B, say C, right? So AND gate you are modeling, when you are modeling your gates logics, you are having the gate, say this is the 2-unit delay, this OR gate having the 2-unit delay, I mean output reflect after the 2 nanosecond delay. Similarly, this is having the gate delay of say 1. So hash sign is used for the delay. Hash sign in the Verilog is used for the delay. Right? Delay of the 1. I mean 1 means maybe nanosecond, picosecond, that depends upon your unit. Okay. So how to model it? Say suppose C. So what you do in the, I am not writing here, like you do the OR gate followed by your delay 2 and instance name say OR1 and do the port connections. Okay. Similarly, AND gate you have to delay unit, you have to give 1 and instance name say AND1, do the port connections. So this way you can get your designs with the delay, having the delay units. Okay, delays. But if you approach this way, this is the zero delay model. There is no delay assigned to it. Okay, right. So now for example, I am talking about the 4-bit adder design. Similar approach we are being followed, we will come to the top to bottom and we will go to the bottom up. Okay, in the top to bottom 4-bit adder is having the 4 full adders, you know it, right? Each full adder is having, can be divided into the 2 logics, one is a sum logic and another is the carry logic, right? Each, no, now the sum is can be designed using some logics, and carry is also you can design using the logics. Say sum is a or x or b x or b to the c, or sum in the a, like what is the a and b and the c into a plus b. So these are logics. You have to declare the design your sum and carry and integrate the full adder and go to the 4-bit adder. So in the module, how to write it? I mean Verilog. In the Verilog, you design first sum, right? I have designed the sum using the XOR gate and carry using this AND OR logics. Okay, this carry and sum I using these modules I integrated for the full adder, right? This full adder. Again using this full adder, these full adders I have instantiated for the 4 times. 4 times I have instantiated, right? So this instance names is a unique A0, A1, A2, A3. So corresponding connections I have done, right? You can take as a assignment, in the first class of your Verilog. When you go to the lab, you design your 4-bit adder, 4-bit full adder. This is your assignment. First class I will see you, you have to design the 4-bit full adder. Okay, so this is the, this way you can integrate, you can design your 4-bit adder, 4-bit full adder. So now we will have a break, and after 10 minutes we will start the other 2 designs. Okay.